All right, so 5.1, separable differential equations. Separable differential equations. We're going to be solving separable differential equations, but we have already seen differential equations, right? What is a differential equation? It's an equation, yeah, very good, that has a, oh, well, you can take the derivative of it. Oh, not necessarily. No, it's basically an equation that has a what in it? Derivative. A derivative. So if I just say like f prime of x equals 2x, that is a differential equation because it equates two things, it has the equal sign, and it also has a derivative in it. Okay, that's a differential equation. If I have dy dx, maybe even make it this, equals 3x, that is what we call a second order differential equation. This one on the left would be a first order differential equation. So the number of derivatives in it you can classify by order. And what does it mean to solve a differential equation? We've done that too. If I ask you to solve f prime of x equals 2x to give me the general solution, remember it means getting back to the original equation. So you would anti-differentiate both sides. The left side would become f of x, and the right side would become x squared plus c. And remember, we called that not that long ago the general solution. And if we needed to find the value of c, you would need to be given what? Some point that satisfies the equation, some initial condition, and then you can plug it in and find the particular solution. So solving a second order differential equation like this one would mean getting all the way from the second derivative back to y equals. And if you were interested in finding the particular solution, remember you would need two pieces of information so you can find each of the constants as you integrate. So we did that in 4.2 or 3 or somewhere in there. Well, this whole section is going to be dealing with differential equations like this that are a little bit more interesting than that. So what makes them separable is in the sense that we can get a function of y with respect to y on one side, and we can get a function of x with respect to x on the other side. We can basically separate the y's and the dy's from the x's and the dx's. And not all differential equations can be separated, which means they're not going to be able to be solved at this level analytically. So in this section, we're going to be solving these types of equations. Because if I could separate the variables, and I can get a function of y with respect to y on the left, and a function of x with respect to x on the right, then I can essentially integrate both sides. And when I integrate both sides, I would get like big F of y over here, plus c sub 1, and big F of x over here, plus c sub 2, and then I can solve for big F of y by subtracting c sub 1, and combining my c's to get new and improved ShamWell c. So that's essentially what we're going to be doing. All right, but what's important here is that we show the separation of variables, as you shall see. Okay? So blah, 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 blah. Example 1. The graph of several solutions to the differential equation dy dx equals x squared over y squared is shown. Now, before we look at the graph, I didn't have to tell you that was a differential equation. You would know it by looking at it because what? It has a derivative in it, right? This would be a first order differential equation because it's a first derivative, okay? Now notice what's different about it immediately. It's dy dx equals, and on the right-hand side, we have what? We have an x squared and a y squared. And we haven't seen any differential equations yet that had both x's and y's on that side. But this one does, okay? So here's what the general solution curve looks like, all right? And notice that it looks like an onion bulb. These are all going to be different particular solutions depending upon different initial conditions through which a function must pass. So let's say I know that one of the solutions has to pass through that point right there, then the particular solution would look like that. if I know that a different particular solution would have to pass through, let's say, this point way down here, then this right here would be what the graph of it looks like. And it's interesting to note at this point that if you had a function that passed through the origin, it wouldn't be curved at all. It looks like it would just be a horizontal line. And each of those are going to be differing by an initial condition. All right? So here's what we're going to do. We're going to actually solve that differential equation. And we're going to find the particular solutions, that is, the equations of some of those functions up there. All right, so step one, it says to solve the equation and then find the particular solution. You have to find the general solution before you find the particular solution. If we come back up here, this is the general solution. It has the plus c. Once you have that, then you can use your initial condition to find c. All right? So let's do that. Let's try and find the general solution to this differential equation. Well, it's going to be a little bit more involved than what we've seen. Okay? If I just take the antiderivative of the left side, the antiderivative of dy dx is y, right? But how do I take the antiderivative of x squared over y squared? Do we know how to take the antiderivative if there's more than one variable? Implicit antidifferentiation. Whoa, that's going to be hard, right? Because I remember implicit differentiating going forward was kind of messy. Going backwards is going to be a little bit hard. That's what differential equations is all about. How can we solve that? And there is kind of a way to do implicit differentiation, but it's beyond the scope of what we're going to do. So in this case, if we can somehow separate the x's from the y's, maybe we can just treat it as two separate integrals, one in terms of x and one in terms of y, and then just rely on what we already know. Okay? So that's what we're going to have to do first. We're going to have to show the separation. And remember, there is a rat in separate. We're going to have to show the separation of the variables. And it's going to be pretty easy typically. Like in this case, you have a proportion, and if you just cross multiply, you've accomplished the goal. All right? So I'm going to multiply both sides by dx, and I get x squared over y squared times dx. Now what that did in one step is it got rid of the x's from the left. But notice, Schroeder, I still have a y on the right. So now if I multiply both sides by y squared, it's going to divide out on the right, and I get a y squared dy equals an x squared dx. Now you could do that in one step. Did we show the separation? Yes, okay. Now that's going to be an important step. It's going to be a very important step because it earns you a check, but it can also cost you up to 6 checks if you don't show it. Now typically when we separate the variables, we could treat those as individual factors, and multiplication is commutative, but we want to go ahead and put our dy and dx as the right bookend, because once you separate the variables, the next step is to integrate both sides. Okay? You're going to integrate both sides. And now, because we've separated the variables, we're integrating each side with respect to their own variable, which makes it easy. We don't have to do implicit antidifferentiation. So what would be the antiderivative of y squared with respect to y? 1/3 y cubed, and then, of course, plus c. Now, I'm going to put plus c sub 1, so we don't have to use two different letters. We use subscripts instead. On the right side, x squared becomes 1/3 x cubed plus c sub 2. Yeah. Now, that's going to earn probably a check on either side. Maybe just one for the whole thing. Is that solved? Did I just solve? Did I find the general solution? The general solution means solving for your dependent variable, which is always the one in the numerator up there. So I need to solve it for y. So now I need to algebraically solve it for y. How do I do that? A little algebra now. Bring the c over. So I got 1/3 y cubed equals 1/3 x cubed. And I'm going to have c sub 2 minus c sub 1, which is new and improved c. Yes. Now, here's the thing. In general, because we are going to be collecting our information on the independent variable side, you can go straight from that step to that step. In other words, you are not going to lose points if you don't show the c sub 1, c sub 2. If you just rather show the plus c, as soon as you take the antiderivative, if you show it on the side of your independent variable, we understand why it's not shown there, okay? So that's permissible. But you understand why we can do that. Because that unknown constant just becomes a new and improved unknown constant. All right, so now I'm one step closer to solving for y. What would I do next, algebraically? Yeah, multiply both sides by 3. So it's going to give me a y cubed over here. And when I distribute on the right side, I get 3 times a third, which is 1. So I get x cubed plus 3 times c. 3 times an unknown constant is another unknown constant. ShamWow c, super absorbent. It just absorbed that 3. ShamWow. Now, how do I solve for what? Cube root it. Okay? Now, when I cube root it, is the plus c under the radical or outside the radical? Can it absorb the radical? No. You treat it like a constant. It can absorb things added to it. It can multiply factors that are multiplied by it or divided by it. But you still treat it like a constant. So it's underneath the radical. Do you need to consider plus or minus when you take the cube root? No. Okay, did we solve it? Do we have y equals a function of x? We did indeed. This is the general solution. Okay? And you would earn points for that. General solution. Now, to get a particular solution, we need to have some information about the original function. Well, that's what parts A, B, and C are. On part A, it says that it's passing through the point 0, 2. Let me rewrite that. 0, 2. So how are we going to find C? Well, it basically says, and this is kind of like hybrid function notation, f of 0, y of 0. When x is 0, y is 2. So all we got to do is plug in a 2 for y and an x for 0. And this is how we'll show it. You can just say y of 0 equals 2, and underneath there put 2 equals the cube root of, plugging in a 0 for x, we get c. Okay, so that's c. And then how do we solve for c? By the way, at this point, since we've plugged in the cube root of c, you do not want to call it new and improved c at this point. Because at this point, c is the variable that you're trying to solve for. And if you let it absorb at this point, you're not going to get the right value of c to plug back in up there. So it can absorb things up until the general solution. And once you get to your locked-in general solution, now that c has to be treated as a true constant. Okay? So now to solve for c, you would have to cube both sides, and you get 2 cubed, which is 8. All right, so you would earn another check right there. So the particular solution is y equals the cube root of x cubed plus 8. All right, now let's do something here. Let's graph that. The solution that passes to the point 0, 2. I think I've already done that, but let's get rid of all this up here so we can see it in it alone. Let's say that 0, 2 is right there. So that's going to be this middle one. So I claim that that is a function. It still passes the vertical line test. Barely. It looks like it might go vertical, but it passes the vertical line test. And I claim that the equation of that graph is that one. Would you believe me? You should, because you did it with me. But let's see if the calculator knows that as well, or whether it can confirm that after it confirms the software license, which it always does. And it takes like 3 years. Bouncing on a pogo stick. While I'm doing that, go ahead and jump on part B. See if you can do the same thing for 0, -2. And I'll go ahead and type it in, and then we'll meet you back here. At least you'll have the equation ready to go. Not cooperating today. There it goes. Just a little slow. All right, keep working if you're in a groove here. I'm just going to type in the equation we got on part A, the cube root of x cubed plus 8. So I'm going to type that in as the quantity x cubed plus 8, and then I'll raise that to the 1/3 power. Now, because we have a graph of it already over here in a nice window so we can compare, let's go ahead and do the same thing. Let's go from -3 to 3, and it looks like we'll count by ones. That looks good. And -3 to 3. And when I hit graph, I should get something that resembles that, except it's blue instead of green. Yeah. Looks pretty good, huh? Looks pretty good. So yeah, there you go. It still is a function of x, which is interesting to note because notice the derivative or the differential equation that we had was not a function of x. It was a function of both x and y, but it still gave us a graph that became y equals a function of x exclusively, so it still passed the vertical line test. That's not always the case either. All right, so let's do part B. To do part B, you don't have to reinvent the wheel. All you have to do is go back to the same general solution and plug in a different point. So you could do it differently. You could say at 0, -2, instead of saying y of 0 equals -2. And if you plug it into the general solution, you get -2 equals the cube root of c. Now again, the cube root of c at this point, you don't want it to absorb the cube root of an unknown because you are finding what c is in your locked-in general form. So if you cube both sides, you get -8. So the particular solution will be, very similarly, the cube root of x cubed -8. And if I graph that in y2, let's see what I get. I should get, oops, -8 to the 1/3. Hit graph. This one will show up in red. It's passing right through -2 perfectly, and there it goes. Yeah, so we're creating that onion bulb. And if you wanted to compare it over here, maybe now with the same color, yeah, it's looking mighty good there. I'm going to go ahead and change this one. What the heck? Style. Let's do blue. Now it matches. Change this style. Make it thicker. Make it thicker. Okay, whatever. So now it looks kind of like the calculators. And then the last one, the one that passes through 0, 0. Now let's do something else here, and we've already kind of looked at it. The particular solution that passes through 0, 0, as we've already seen over here, what would be the next color? Pink. You can see what the graph looks like, right? It looks like it's not going to be curved. Oops. It's not going to be curving at all. It's going to simply be y. It looks like it should be y equals x. Now, how in the heck are we going to get y equals x out of something that looks like that? Well, we shall see on part C. At 0, 0, we get 0 equals the cube root of 0 cubed, which is 0, plus c is c. Cube both sides, you get c equals 0. So, y equals the cube root of x cubed plus 0. Well, what is the cube root of x cubed? X. There you go. So it works out. Pretty neat. And of course, if we have a different ordered pair through which we would like the graph to pass, we could plug it into the general solution here and find its value of c, and therefore we can find its ultimate equation. So again, ShamWow C can absorb things that are added to it, subtracted from it, multiplied by it, divided from it. You could even say the square root of c is new and improved c up until you get to the general solution. But then you have a locked-in form, and then when you're finding c, you're treating it like the variable of interest, and you have to treat it like a true constant and solve for it. And then, whatever you find c to be, you plug it back into your locked-in form up here. All right? And you'll always come out with an equivalent answer. Because you could actually have different versions that come up with different values of c depending on what your locked-in final form looks like, but they will end up being equivalent. And we'll kind of explore that as we go. So there's the idea behind a separable differential equation. It's a differential equation that has a derivative in it. And typically, but not always, the derivative is a function of something that's more than just x. Maybe an x and y, maybe it's just y. And by separating the x's and dx's from the y's and dy's, we basically turn it into two separate problems, both of which we can do. Find the general solution first, and then find the particular solutions. All right, questions on number 1? Got the idea? It's just anti-differentiation. All right, number 2. Find the general and the particular solutions to the separable differential equation dy dx equals x squared, given the initial conditions. F of 0 is 1 and f of 0 equals -2. Okay, so in this case, we don't have the luxury of the graph to see what it looks like, but I don't think we need it. So how do you know this is a differential equation other than you read? It's got a derivative in it. Yeah, good. And this would be, again, what we call a first-order differential equation. Now, you're not going to be asked to solve a differential equation that is not separable. Keep that in mind. Because if you can't separate the x's and dx's from the y's and dy's, at this level, you cannot find the antiderivative. So you will not be asked to do that. There is going to be a way to still see the solutions when we can't separate the variables, but that's coming in the next section. All right? So that's the first step. I need to separate the x's and dx's from the y's and dy's. So if I multiply both sides by dx, I get x squared times y times dx. And that's typically always one of the things you're going to do, right? Because dx is always going to show up in the denominator. Did that do it? That separate the variables? Nope. I still got a y on the right-hand side, so if I divide both sides by y, I get 1 over y dy equals x squared dx. Did that do it? That did it. So that would earn a check right there. Congratulations, you've separated the variables. What would be the next step then? Integrate, right? You're going to integrate both sides. And it goes in the front. So you should have your integral in the front and your bookend dy or dx, your differential at the back end there. All right, so what becomes of the left side? We're just focusing on this. Remember, the variables don't matter as long as they match. 1 over y with respect to y becomes ln of absolute value of y. Do we need the plus c on the side of the dependent variable? No, we don't. Okay, and then this side, of course, is 1/3 x cubed. Do we need a plus c on this side? Can we just add it later at the end, or do we need it now? Sure, you better put it now. You can't just solve for y and then say, oh yeah, plus c. Okay, you need it as soon as you find the antiderivative. Now, in the process of solving for y, this can be ShamWow C. It can absorb things. But once you get y equals, it's locked in. All right? Okay, then. We need to solve for y algebraically. The calculus is over for now. We just need to do some good old algebra. How do I solve for y? Do I divide by ln? Absolute value, both sides? How do I un-ln? E both sides. E to the that equals e to the that. Exponentiate both sides. So e to the natural log of blob is the blob. What is the blob? Y? It's still absolute values. They don't just go away when you eat it. They're still there. Now, on the right side, I have e to the blob. There are two routes you could take from here. Both are correct. I will show you both versions. You can either preserve it as a 1/3 x cubed, and this gets a little bit, let me go smaller on my fineness here. You can, I'm going to call it x cubed over 3 plus c. That would be the exponent. That gets kind of cluttered up there, right? The other way to do it, or the absolute value of y equals e to the x cubed over c times, that's not the right way, my bad. Sorry, thinking ahead. X cubed over, c and 3 rhyme at least, right? And then times e to the c. Does that work? Yes. Okay. Again, we're used to going from the right side to the left side. When you are multiplying and the bases are the same, we typically add the exponents. But when you're adding exponents, you can multiply and give them each their own base. So the one on the right is going to be preferred. for a couple of reasons. The first reason is it doesn't clutter up the exponent as much because that plus c, he's cantilevered out there on the exponent. And he can tend to fall down on the ground floor. And if that guy accidentally falls down on the ground floor and you just put a plus c down here, that is now RONG wrong, okay? Because it's the sum of two things rather than the right side, which is really a product. So there's the risk of doing that. The other benefit you'll see in just a second here. Okay, so let's go ahead and simplify the right side. I'm still in the process of solving for y, so it's still super absorbent ShamWow C. So what is e raised to an unknown constant? It's another unknown constant, isn't it? Okay, so I'm multiplying now by this new and improved c, which I'm going to bring it to the front. So I get c times e to the x cubed thirds. Now here's the thing. When you drop the absolute values from an equation, and I'm going to jump back over the left here, you have to consider plus or minus. That's how you get rid of the absolute values. So it's plus or minus e to the x cubed thirds plus c. And maybe if you want to make sure that he doesn't fall to the ground floor, you put parentheses around it. Okay? Now that's the general solution. If it ends up being positive, then the e graph is going to open upwards. If it ends up being the negative solution, the e graph will open downwards. Okay? Now look at us over here. When I drop the absolute values over here, I have plus or minus c e to the x cubed thirds. Do I need plus or minus c, though? Over here, I needed the plus or minus because there was a 1 in front implied, right? And 1 is always positive. But c is an unknown, isn't it? And by the nature of being unknown, c could be positive or negative depending on what it is, right? That makes sense. So here's the extra benefit of bringing that c. You not only get rid of the cantilevered c that could fall down, you don't need the, well, you need the c. You don't need the plus or minus in front. You don't need the plus or minus in front because c itself is an unknown coefficient which could be a positive number or a negative number. And it makes it look a little bit more tidy. They are both correct. So notice the equivalencies here. You either have a sum in the exponent or a scalar multiple times e. But you do not have, like I said, this. You don't have e to the x cubed thirds and then a plus c right here. It's not a sum of two things, okay? Now, either one are correct. Let's go ahead and then find the particular solution at 0, 1. And you'll see that they both work. So we'll do both of these. So part A, I'm going to switch to a little bit bigger now. Part A, at the point 0, 1. You still want to make some kind of notation that you're plugging it in. So I get 1 equals plus or minus e to the. Now when I plug in, when I plug in a 0 for x, I get 0 cubed, which is 0 divided by 3 is 0. I get e to the cth power. That's kind of funny. Now, do I want to call e to the cth power new and improved c here? No, because I'm locked into that form. So how do I solve for c? Take the natural log of both sides. So I'm either going to have 1 equals positive e to the c or 1 equals negative e to the c. So if I take the natural log of both sides, I get the natural log of 1 equals the natural log of e to the c, or that's an on, or the natural log of 1 equals the natural log of negative e to the c. Well, what's the natural log of 1? 0. And over here I get c equals 0. Now over here, I'd have to expand that. The natural log of 1 is 0, and I get the natural log of negative 1 plus the natural log of e to the c, which is c. What is the natural log of negative 1? D and e. So this one doesn't work. Okay? So I get c equals 0. Now notice that's the value of c. It's not a different one. We haven't done the other one yet. Sorry. I'm thinking ahead. But once I find that value of c, because I got it from this form, that is the form into which I must plug. So the particular solution is going to be y equals e to the x cubed thirds plus 0, which is x cubed thirds. Now, here's the thing. This is the other reason why we're eventually not going to be doing it this way. For your particular solution, you can't leave a plus or minus in there. You cannot. You have to commit to whether it's plus or minus. It can't be both because it's not the general solution, it's a particular. And if you left it as plus or minus, that's 2. So how do you know whether it's going to be plus or minus? You have to plug in your ordered pair and make sure that when you plug in a 0 for x, you're going to get out what type of 1? A positive 1. So if I plug in a 0, I get e to the 0, which is 1. It needs to be positive. So there is your solution. If it turned out that it was the point 0, negative 1, then I would need to have a negative in front there to get that. So there's your particular solution. So this method right here, we are not going to do it this way. But it works. Okay, don't do it that way. But it works. Okay, we're going to do it this way. Part A. At the point 0, 1. Now look how much easier this is going to be. We're locked into this general form now, which is a little bit different. But you'll see that we get the same answer. We get 1 equals c times e to the 0. And of course, e to the 0 is what? 1. Yeah, 1, right? And what's 1 times c? C. And what's c plus 0? C. Yeah, okay. We get c equals 1. Is that the same c value we got over here on the other part? No, we got c equals 0. Which one is correct? They're both correct. Because they're both coming from a slightly different but equivalent general form. And that's why it's important. Once you get to your general form, you're locked in on that. You might get a different value of c. But when you plug it back into your locked-in form that you used to find your c, you'll get an equivalent answer. Now notice this takes all the ambiguity out of it because I get c equals 1. And when I plug it in there, I get so y equals what? What kind of 1 did we find? Positive 1. E to the x cubed thirds. So we don't have to plug back in and decide if it's plus or minus. Minus. It comes out in our calculation. So this is the way we will do it. We will do this way. Yes. Okay. How does this score on a free response? And this makes a great free response question, by the way. It's at least 5 points out of 9, sometimes 6. You get a point for using the initial condition. Okay? So as soon as you plugged in your ordered pair to your general solution, whichever version it was, that's where you get the check. It's not for a particular value of c. You could even have the wrong general solution. You could have kind of goofed up. If you're plugging in to find c and it's close to what the real one is, you're still going to get the check for using the initial condition to find c. Of course, y'all are going to be so well trained, you're going to be finding the right one. But there are multiple c's that could work depending on your locked-in form. Correct. Yes. All right, let's go ahead and do the second one. All right, so now I'm going to reuse the general form that we prefer, ce to the x cubed thirds. That's the general form that we prefer. So we'll say at the point 0, negative 2, we get negative 2 equals c e to the 0th. E to the 0 is 1, so c equals negative 2. So we get y equals negative 2 e to the x cubed thirds. And if you had done it the other way, you would have to then test the point again after the fact to decide if it was positive or negative, because you wouldn't have a c out front. Your c would be a different c that would be absorbed up in the exponent. So remember, a sum or a difference in an exponent is the same as a constant multiple out front. That's kind of an important thing to remember. And it makes sense, because in order for our exponential function to pass through a negative y value, we would have to have a negative in front, because that reflects the function across the x-axis. And if you're not sure if it's right or not, just quickly make sure. When you plug in a 0, do you get a negative 2? We do. Got it. So once again, we started with a differential equation that was not a function of x exclusively. It was a function of both x and y. But we were able to separate the variables, and we were able to solve it as a function of y in terms of x. Pretty nice, pretty nifty. All right, let's look at one from an actual AP exam. Way back in 1998. This was question 4 on the free response. Okay. Let f be a function with f of 1 equaling 4. Okay, I'll let that happen. Such that for all points x, y on the graph of f, the slope is given by this. Okay, so notice that it's a differential equation, and it's in terms of both x and y. We've got x's in the top and y in the bottom. Part A, find the slope of the graph of f at the point where x equals 1. Okay, find the slope at a point, slope at a point, slope at a point. That's the ¿cómo se dice? Derivative? Pendiente? No. The slope at a point, that's the derivative, right? So, notice your derivative, though, unfortunately requires not just an x, it requires a y as well, and they only gave me an x value. How am I going to find the y value at x equals 1? Hey! Yeah, boom, there it is. Thank you, College Board. College Board, why didn't you just do A for me? Notation, notation, notation. No notation? No points. dy dx, whole n bar, and you could use the ordered pair 1, 4, something like that. That's good. Or you can say at 1, 4, or 4f of 1 equals 4. Something that indicates that you are plugging in a number into your variable. And now, this is the best way, if it's a function of 2 variables. So now we just carefully plug into the correct values, x plus 1 all over 2 times 4. And maybe I'll put in parentheses instead of dots so it doesn't look like a decimal. And I'm walking away. Are there any units we need to put on there? No, we're good. Okay, so we can sleep at night. 4/8, 1/2. Doesn't hurt, right? But do you get bonus points for that? No. But it might be easier if you're asked to like describe what's happening, or you need to use that for some subsequent calculation. It's worth simplifying. Okay, that's it. That was easy. That was part A. We're ready for the AP exam, aren't we? That was easy. Part B, write an equation of the tangent line at 1. Okay, that's easy. And then use it to approximate f of 1.2. Oh, what kind of alert are we on? Squiggles. Squiggle alert. Squiggles. All right, what do we need for the equation of the line? Slope and a point. Slope and a point. At x equals 1, do we have the point? Yeah, the point is 1 comma, gosh, what is it? Oh, they gave it to me still. 4. And the slope at that point. Hey, we just found that at A. It's almost like College Board is just like guiding us towards where they want to take us. Little breadcrumbs. It's 1/2.
Excuse interruption. Quickly before our video announcements, a couple announcements. First of all, we want to wish everyone participating tonight in athletic endeavors good luck. Got a lot going on tonight. The men's basketball team's playing at home against Canyon. The 6th men has done a great job all year supporting the program, and we appreciate it. We expect a good turnout. We are doing a couple of things. The student section will be underneath our cardboard cutouts. As traditional against Canyon. In addition, we're asking students not to sit on the floor at all, like the last home game against Judson, or to seat in the second row and stand up. And we appreciate you standing the entire game and cheering. Also understand, students, it's about the players. We don't expect you to get into any disagreement, verbal or otherwise, with opposing fans or their players. We're cheering our team on to victory. And after our victory, we're going to be gracious and allow Katie to lead with dignity and respect their efforts on the court, because that's what it's all about. But once again, we wish everyone competed tonight, not just boys basketball, but everyone, soccer, baseball, scrimmage. girls basketball over at Canyon. Everyone else, good luck and wish you the best. And now please turn on, there's more announcements.
Just an announcement about yearbooks for this week.
Following this right here?
On sale for $65. You can make your purchase with Mrs. Wimmer or online at yearbookforever.com. After Friday the 12th, the price goes up to $75.
Ooh.
Okay.
So when you are writing the equation of a tangent line and you're using it, you don't want to just call it generic y, because sometimes y is vague, and are you referring to y the function or y the tangent line? So give it a specific name. That L is fun to make, so I would recommend using it, the script letter capital L.
Also, if you are a part of the
Taylor form.
and you're coming to the boys' game tonight, make sure it's a white out. Wear your white shirt of some sort to represent white out.
White, okay. So don't wear your six-man shirts that you got at the last game. All right, so here's where the notation comes in. The function value, f of 1.2, is approximated by L of 1.2. That's worth a check right there with the squiggles. Then you plug it into Taylor form, and 4 plus 1 half times 0.2. And again, that's a numeric answer. But it works out pretty nicely. Half of 20 cents is a dime. $4 and a dime gives you $4 and a dime. $4.10. So 4.1. 4.1. So far, so good. Nothing too complicated. All right. Part C, find f of x. Find the actual f of x by solving the separable differential equation. You're not going to be asked to solve a separable differential equation if the variables aren't separable with the initial condition, f of 1 equals 4. Okay. So step 1 is to show the separation of variables. If I multiply both sides by dx, I get 3x squared plus 1 dx. Now, here's the thing. You need parentheses there because it's two terms if you're going to put it in the numerator. Do you want to, when you multiply both sides by y, which I think you can see you're going to need to do that, the question is, do you want to leave the 2 on the right side and call it a 1/2 constant, or do you just want to bring the whole 2y over here to the left? Because constant multiples can be on either side. It's the y's and dy's and x's and dx's that you have to separate. What would you do? I would bring it over just because, I mean, it's not wrong to leave it over here, but now you're going to have a 1/2 hanging out here, and whether you distribute it or not, it's nice just to bring it over there, especially if you anticipate what the antiderivative would be, right? So I would bring it across. So that would earn a check right there for the separations. And once you have your y's and dy's and x's and dx's with constants, maybe judiciously chosen to be on either side, you would integrate both sides in front. Now, on the left, 2y becomes y squared. Sweet. That might earn a check, might not. Maybe it's one check for the whole thing. Do you need a plus c on the dependent variable side? No. 3x squared becomes x cubed plus 1 becomes x. That's a check. Sometimes these two are combined into a single check. Sometimes they're separate. Plus c is worth another check on its own right there. Okay? Sweet! Did we solve? Is that the general solution? No. I need to solve for y. Now, when I take the square root, do I need to consider plus or minus? Yes. Plus or minus the square root of x cubed plus x. Where does the plus c go? Outside or inside? Inside. Yeah. He's under the radical. Now, there's no way, like the previous problem, to bring anything out front here to absorb the plus or minus. Okay? If you do, it would be incorrect. There's no correct way to do it, I should say. Okay, so there's the general solution with the plus or minus in front. That might earn a check on its own as well. Now the initial condition is f of 1 equals 4. So we'll say at the point 1, 4, I'm going to set it equal to 4, and I get plus or minus the square root of, and I'm going to get 1 plus 1 plus c. That earns a check right there immediately. As soon as you're using the initial condition, plugging it into your general solution, you're earning a check. All right, so that gives me, how would I solve for that? What would I do to both sides? To get rid of the radical on the right, I have to square both sides, right? And it's still plus or minus there. So I get 16. But what happens when you scare plus or minus? What happens when you square the plus or minus? It becomes positive. So you're left with 1 plus 1, which is 2, plus c. And you get c equals 14. Now, you don't get an extra check for that because they gave it to you up there. So, now you plug it back into the form you use. Y equals, and I leave a little space, x cubed plus x plus 14. Now, because there was a plus or minus in front, we have to commit to one or the other. When I plug in a 1, I need to get out what type of 4? A positive, so that must be a positive right there. Please do not leave the problem without checking, because if that were a negative 4, you would end up with the same value of c, wouldn't you? Because a negative 4 quantity squared would be a positive 16 as well, but you would have to have a negative in front. So it's real easy, especially in nowadays I can see College Board going that route. All right, so there it is. The 14 is under the radical. Now it says to use your solution from part C, that would earn a check maybe, to find the actual value of f of 1.2. Okay. So we're calling that f of x, I guess. So then f of 1.2 is actually equal to the square root of 1.2 cubed plus 1.2 plus 14. Now, could you stop there? You could. It's not very satisfying because what we did up here is we approximated it with the tangent line. Boy, it'd be great to compare it to the actual, but you don't have to. So let's go ahead and, I'm just kind of curious right here. We'll do it without the projector because it takes too long. So 1.2 cubed. 1.2 cubed. Anyone have it? Not yet? Okay, I'll still work on it. Plus 14. I got it almost. I'm almost there. Hang in there. Oh, yeah. You get 4.114365079. Okay? So here's my question to you. If that's the actual value, and we know that now in hindsight, we compare it to our approximation. Our approximation was 4.1 on the nose. So was our approximation an over or an under approximation? It was an under approximation, right? So based upon that, is our function f concave up or concave down on the interval from 1, or in the neighborhood of 1.2, I should say? Concave up. Good. So we can kind of use the result in reverse. Because our approximation was too small, we know the tangent line was below the curve, so it had to be concave up in the neighborhood of 1.2. Good. Now, that was the end of the question. I just added this as a follow-up. What would the solution be if f of 1 equals negative 4? Well, if you were to plug in a negative 4 right here, we'll copy that. When you square both sides, you still get 16 equals 2 plus c. You still get the exact same c value of 14. But because you end up with a negative 4, you would need a negative in front of the radical. And make sure it's all over the radical. And you would need to commit to it, okay? So it's always a good idea to check your ordered pair at the end. When you find your particular solution, just plug it back in and make sure it works. There are 2 times where you're going to get a plus or minus. One of them we saw is when we have the natural log rule of integration, because it generates the absolute value. We need a plus or minus in front when we drop them, or we could bring the c up front to absorb it. The other time is when you're taking like the square root or the fourth root of something to solve for y. Then you're going to have a plus or minus in front. So those are the 2 little caveats to this section that we need to be aware of. Everything else should be pretty straightforward, all right, and particularly fun. So speaking of fun, we'll pick up there tomorrow with example 4, and I'll give you the take-home test at the end of class. Yeah. So have fun at the game tonight. Remember, the student section is where the band usually